In this we can study one of the very important second order linear differential equation called the Cauchy-Euler equation. So Cauchy-Euler differential equation. A linear differential equation, linear differential equation of the form a n x to the n y to the nth derivative plus a to the n minus 1 x to the n minus 1 y to the n minus 1 derivative, like that. So if you're gonna write it like that, then you can write this one as a1 x to the y prime plus a naught y equal fx in general. So what you notice you notice that the xn and the derivative term, they are equal. So this is what we call a linear. This is a linear differential equation, but this is what we call the Cauchy-Euler differential equation of the nth order. Okay, so with let's write with a n minus 1, like that, a naught are constants with a n through a naught constant is called a Cauchy-Euler. It's called a Cauchy-Euler differential equation. But what we can study is the second order Cauchy-Euler equation. So let's write that. The second order Cauchy-Euler equation is, so what happened, we write it like that: a x squared y double prime plus b x y prime plus cy equals 0. So this is how we write it, and we assume that x not equal to 0, because x equals 0 are going to create an issue. So we assume that x not equal to 0. So this is what we call the second order Cauchy-Euler differential equation. So this differential equation has many applications. So let's talk about some of the applications that this has. So this one used to model, for example, stock market, and then what we call the time harmonic motion of a rod. So time harmonic vibration is much better. Time harmonic vibration of a thin rod, and also problems in annular and solid disk. Problems in annular and solid disk. And also if you are in computer science, you can see that analysis of computer algorithms. Analysis of computer algorithms. Such as, so you can see such as quick sort, such as such as quick sort and sorting trees and search trees. So these are like few things, and also like when you try to solve the Laplace equation in the polar coordinates, you're gonna see that. And when solving Laplace equation polar coordinates, so when solving Laplace equation in polar coordinates. So these are like just few examples where you're gonna see this Cauchy-Euler differential equation. And how we gonna solve this one? We normally solve this equation using a special substitution. So so you can say it is solved. It is normally. What is it normally? It is normally solved using a special substitution. So it is normally solved assuming a solution of the form y equal x to the lambda, and then what we can do, we take the derivatives and plug in there and then try to solve for lambda. Okay, so that's what we're trying to do. We assume a solution of the form y equal x to the lambda, and we plug in that to the differential equation, solve for lambda. So it is normally solved assuming a solution of the form y equal x lambda when there are distinct roots, when there are a distinct real roots, when there are distinct real roots to the characteristic equation. And assuming a solution of the form y equal x to the lambda ln x when there are repeated roots. The complex roots situation is like difficult. The case of complex roots. The case of complex roots is complicated. So instead we use a different approach. So use a different approach. So we use a different approach. So what we're trying to do, we actually trying to transform this differential equation to another one which is of constant coefficient. So since we know the solution of constant coefficient, then we can use that to solve this differential equation. So we can transform this differential equation to a constant coefficient differential equation using a substitution. So we can use x equal e to the t. So that's a transformation we can use. X equal e to the t to transform the equation. Transform the equation to a constant coefficient. To a constant coefficient equation when x positive. Okay, so let's do that. How it's gonna work. So what you want to remember is we can use this transformation to change the differential equation to something else that we can handle, that we already know how to solve. So let's do that. So what we can do, we can take the derivatives. So we can start with writing the derivatives. So what we can do, we can write the differential equation not in x, in t. So let's take the derivative. So we can write as so I'm going to write it, let's say dy by dt equal, so we're gonna do we can take the chain rule. So we can write this one as dy by dx and dx by dt. That's a chain rule. Now what we have is we have dy by dx. What is dx over dt? Dx over dt, according to the formula, it is e to the t, but we know that e to the t is simply x, so that means we can write this one as dy by dx times x. So what this says something interesting. This says that x y prime term is in terms of the x variable. So we need to think about what the variable is now. So you can see in terms of the x variable now is simply equals to dy by dt in terms of y variable. So we can write this one as, let me erase this one. You can write this one as simply using the y variable now. So if you use the y variable, this simply equals to y prime t. That's what this says. Okay, good. So let's continue. So now what we can do, we can take the second derivative. So let's take the second derivative. So what we need to do is d squared y over dt squared. As before, let's use the chain rule. So when you use the chain rule, we just take the derivative with respect of the term, so which is dy over dx times x times dx over dt as before. That's the chain rule part. Now for the first term, you have to use a product rule. So we can use a product rule to get this one. So if you use the product rule for the first, you're going to get d squared y over dx squared times x plus, now we have dy over dx, and take the derivative with respect to x, that means 1. So that's what you get from the first term, and then again dx over dt equal to e to the t, but e to the t is simply equal to x. So that means we can write this one as you can see it's not this one, it's e to the t. This is e to the t, but that term is simply equals to, this term is simply equal to x. So because of that, now we can write this solution as d squared y over dx squared times x squared plus dy over dx times x. But we already know what is dy over dx times x from the previous one, so we can substitute for that. So we already know what this looks like, but that's what we had before. So that means using this one, we can simply isolate the first term. So we're going to get this now. So we're going to get, so we are going to get d squared y over dx squared times x squared equals to d squared y over dt squared minus we had dy over dx times x, but this is simply equals to d squared y over dx squared, not dx squared, dt squared minus, but we know that dy over dx times x is simply dy over dt, that we just proved, dt. So okay, so that means we transform the two derivative terms. Now what we can do is we can rewrite the Cauchy-Euler equation using the new variable. Okay, so this is simply, you can write this one as y double prime t minus y prime t. So we can write like that. So now what we can do, we can rewrite the equation using this one. So rewriting, Okay, rewriting the Cauchy-Euler equation in t variable. So what happened? So we had earlier we had a x squared y double prime plus b x y prime plus c y equals, so this is all in terms of x variable. Now what we can do, we can transform this into y variable. So so what happened now is so this term you can replace this one, so that's simply going to be y double prime t minus y prime t. So to exaggerate, this is a t, so we use that t variable there. That's what happened with the first term. And then the second term you can do similarly. These two terms also you can replace now. So what's going to happen now, plus b. So what happened, that term is simply y prime t, so that's simply going to be y prime t. So this is y prime t, so that's what you get, plus, and then c, so it's a function of x before, now it's a function of y, so it is ty, and so that's what you get. So so in other words, if you collect the terms, you can see that's you can write this one as a y double prime t, and then you can see y prime term you can combine, so you're going to get b minus a y prime t plus c y t. Now we know that originally this was equal to 0, so this is equal to 0. So you can see that you simply get a constant coefficient differential equation in terms of the t variable, which you know how to solve, that we discussed. So this is a so we have, so I'm going to write this equation. So what we have now is this one. So we have a y double prime t, just a variable, plus b minus a y prime t plus c y t equals 0. So this is a constant coefficient differential equation. That's what it gets. You transform this differential equation to something easy. So this is a constant coefficient. So the constant coefficient differential equation. So that means what we normally do is we can look at the characteristic equation. So the characteristic equation of this one is characteristic equation is simply we can replace the derivative by the lambda. So it is a lambda squared plus b minus a lambda plus c equals 0. So that's the characteristic equation. So we have this characteristic equation. Now what we can do, we simply solve this as a constant coefficient differential equation as we did before, and then at the end we can transform the solution to the new variable. So let's do that. So we're going to consider we go case by case. So we have, if b minus a squared minus 4ac equal to 0, then we have a real distinct solution. So we have two solutions, r1 not equal to r2, so that means these are real and distinct, and we know how to write the solution. So the solution of this one is simply y equal c1 e to the r1t, this variable is t now, plus c2 e to the r2t. So what we can do is we can use some nice algebra, because we know that we can write this same term. Just recall some of the algebra, like we know that if you have a m n, you can write this one as a to the m n or a to the n m. So we can use this idea here. Now the product you can write as a power, so that means you can rewrite this one as c1 e to the t r1 plus c2 e to the t r2. But we know that from the substitution, e to the t is simply equal to x. We know that e to the t is simply equal to x. So that means you can replace that, then you're going to get the solution as simply c1 x to the r1 plus c2 x to the r2. So that is the solution when the b minus a squared minus 4ac greater than 0. So similarly, let's look at the second case. If b minus a squared minus 4ac equals 0, we have two equals. So we have r1 equal r2. So that means the real equal situation. We know how to solve real equal. So real equal means your solution y is simply equals to c1 plus c2t e to the r1t. So we do the same thing as before, but what you can do right now is we have c1 plus what is t, because we know that x equal e to the t. If x equal e to the t, if and only if t equal ln x, because we assume that x is positive, so you can do that. So that means you simply replace all the t's by ln x and e to the t by x. So if you do that, then you end up getting c2 t is equal to ln x times, as before, this one you can write as x to the r1. That's the exact same thing that we did before. Okay, so that's a solution. You can write it like this, or you can split this and write two solutions, but that's the general solution looks like. So the third case, in the third case, what's going to happen if b minus a squared 4ac is negative. If this is negative, then you can write, then what you're gonna happen is your r is gonna be alpha plus or minus I beta. That's the solution, how the solution looks like. So you have the complex conjugate situation. You have complex conjugate. So in the complex conjugate, you know how the solution looks like. So the solution looks like y equal e to the alpha t. Remember the differential equation in the variable t. Okay, so you solve in t first, and then c1 cosine beta t plus c2 sine beta t. Now as before, what we can do, we can replace all the t's by ln x and e to the t by x. So that means if you do that, then you're gonna get this one you can write as x to the alpha, and here you can write this one as c1 cosine t is equal to ln x, so we can write beta ln x plus c2 sine beta ln x. So that's how the general solution looks like when b minus a squared minus 4ac equal negative. So you can see that so this is the kind of easy way to do it. So you're going to consider three separate cases, and then you can write the general solution in those three cases simply applying the constant coefficient differential equation. So it's gonna make it much easier, because you transform the differential equation to a constant coefficient differential equation, and then you use the results from that. Okay, so yeah, so the three cases that we considered here is, so we consider this one. So remember, it's not just b, it's b minus a, and then we had this one, and then also we had that one. So we need to consider three cases separately and get those three general solutions, and you can apply them directly when you have problems. So you only need to figure out what cases you have out of those three cases. Okay, now what's going to happen? So we only consider a situation where x is positive. So now what we can do now, for x negative, we use x equal negative e to the t. That's how we try to do. We use x equal negative e to the t. So there's something interesting happen, and we can see that even in this case, once you try to take the derivatives and plug in, you end up with the exact same differential equation. Okay, so now for example we use x equal negative t. So what happen is we're gonna get the even in this case we're gonna get the exact same differential equation. It's kind of interesting. So it can be seen that we obtain the same constant coefficient equation. We obtain the same very important, same constant coefficient we obtain the same constant coefficient differential equation. Therefore thus the solutions can be simply obtained by replacing x with negative x. So that's what I do. So we simply replace x by negative x to get the solutions in this case, because you get the exact same differential equation. So we can say, therefore we can write the general solution. Okay, therefore when x not equal to 0 with a positive or negative, the general solution take the form so let's say one by one. So the first case, if b minus a squared minus 4ac positive, then you're going to get the solution as y equal c1. We write just the absolute sign because it contains both solutions, whether positive or negative, because when x is negative x equal to positive, so that means you just write the absolute value. So r1 plus c2 absolute r2. So that's for the b minus a squared minus 4ac positive, and if b minus a squared minus 4ac equal to 0, you're going to get the solution as y equal c1 plus c2 ln. We write the absolute sign because it can be negative now, so we put absolute ln absolute x, and again here also absolute r1, absolute x r1. And then if b minus a squared minus 4ac negative, you're gonna get y equal x to the alpha, again absolute x because x can be positive or negative, and then again here c1 cosine beta ln absolute x plus c2 sine beta ln absolute x. So that's how the general solution looks like in those three cases, and you can write these solutions directly, but this is for the general x. So when you get a problem, see whether we are solving for positive x, whether we are solving for negative x, or we are solving for general x. Okay. and then I'm gonna put a like small note here. So we cannot solve the equation. We can solve the equation for x equal 0, since there is a singularity at x equals 0. We can discuss this later, what is a singular point means. So that's the end of the theory part. Now what we're gonna do is we're gonna use this for, so you can directly use this result. We can use to solve few problems. So let's start with something easy first. So the first example. So example number 1. So let's say solve x squared y double prime minus 2x y prime minus 4y equal to 0 for x positive. So that means not the general case, it's just the first case. So you can see that here what's going to happen is a equals to 1, b equals to -2, c equals to -4. So the characteristic equation of the transformed equation is, it is a lambda squared plus b minus a lambda plus c equals 0. So we're going to plug in. So that means it's going to be lambda squared minus b minus a. B minus a become 3, -3, so it's a -3 lambda minus 4 equals 0. We're going to factor. This is very easy to factor. So what are the factors? Lambda minus 4 and lambda plus 1. So this is going to give you lambda equal -1 and 4. We normally write the smaller one first. So those are the two solutions. They are real distinct. Okay, so real distinct. So since real distinct is the first case, so the general solution is y equal c1 x to the r1 plus c2 x to the r2. So if you plug in here, so you're gonna get c1 x to the r1, one is 4 and the other one is, so the c2 x to the other one is -1. So -1, you can write this one as, you can leave it like that, or you can write this one as c1 x to the 4 plus c2 over x. So this is for x positive, and you can see that x cannot be 0 here because you're dividing by 6. So that's the general solution to this differential equation. Very good. So let's try to do another one. So the next one, so example, so solve, let's say x squared y double prime plus 5x y prime plus 4y equals 0. So let's say general case, s not equal to 0. Let's solve for general case. So again we can identify what is ABC. So a equal 1, b equal 5, and then c equal 4. So then again the transform characteristic equation is a lambda squared plus 5 minus 1 lambda plus 4 equals 0. So so you're gonna get what do you get? You're gonna get lambda squared plus 4 lambda plus 4 equals 0. So this is a family equation. This one you can write as lambda plus 2 lambda plus 2. So that means it's going to give lambda equal 2 comma 2. We write it like that just to exaggerate this repeated. So the real repeated situation. A real repeated, then we know what the solution looks like. So the therefore the general solution is therefore the general solution is given by y equal c1 plus c2 ln absolute value of x times the absolute value x lambda 1. So what is the lambda 1 here? So this is c1 plus c2 ln x, which is x lambda 1 equal to 2. So this is for x not equal to 0. So that's the general solution looks like for this Cauchy-Euler differential equation. So let's do another one from from the last type. So the complex situation. So example, so we have, so let's say solve, let's say 4x squared y double prime plus 17 y equals 0 along with y1 equal negative 1 and y prime 1 equal negative 1/2. Let's try to solve like little complicated one. This is the we can solve a second order initial value problem. So the answer is, so here we can see that a equal 4, b equal 0, c equal 17, and as before the transformed characteristic equation is 4 lambda squared minus b minus a, that means negative 4 lambda, plus c 17 equals 0. So we try to find factors. So the best thing would be use the quadratic formula. So we can use the quadratic formula. So if you use that, it is negative b plus or minus b squared minus 4ac square root over 2a. So if you plug in here, so you're gonna get you are gonna get 4 plus or minus b squared means 16 minus 4ac square root over 2a, which is 8. So it is 4 plus or minus. So what's gonna happen? You can see 4 times 4 is 16. If we pull out 16 out, so it's a 16 times negative 16. So that's what you get. So and then once you take the square root, you're gonna get you can say 16. So so you can write this one as, so just inside you can do some algebra, because 4 times 4 is 16. So if you pull out 16, so you're gonna get 16 times 16 squared. So you're gonna get 16 squared negative 16 squared. So you're gonna get the square root negative 16 squared. That's what you get. And then you can use the complex numbers to solve this now. So that means if you do that, in the top you're gonna get 4 plus or minus 16i over 8. If you divide by 8, then you're gonna get simply 1/2 plus or minus 2i. So that's the what you get. So then, so that means alpha is equal to 1/2, beta equal to 2. So this says that alpha equal to 1/2, beta equals to 2. So that means we can write the solution. So y equal simply x 1/2 c1 cosine 2 times ln x plus c2 sine 2 times ln x. So we just go for the x positive case. The reason is initial conditions are given at 1. So good. So that's the general solution. So this is the general solution. Now what we want to do is we want to solve this for C1 and C2. So we can use the initial conditions for that. So let's use the first condition. So if you use the first condition, you're going to get so using the initial condition, so we have y1 equal -1. So if you use that, you're going to get -1 equal 1 to the 1/2. So I just plug in where you see x equal 1. So then you're going to get c1 cosine, we know that ln 1 equals 0, so you get 0 here, plus c2 sine 0 for the same reason. So that means this says that c1 equal -1. Now we can plug in that to the equation and take the derivatives. So the taking derivatives, so that means your differential equation looks like this now. So we're going to say yx is equals to 1/2 no. So your differential equation looks like x to the 1/2 x to the 1/2 c1 equal -1. So whatever you know, you're going to plug in. So it's going to make it easy to simplify. Ln x and then plus c2 that we don't know yet, sine 2 ln x. That's what we have. Now what we do, take in derivatives. So if you take the derivatives, you're going to get y prime x which is equals to 1/2 x to the -1/2. So let's use the chain rule here. If you use the chain rule, you're going to get negative so we have the so first actually we have to use we have to use the product rule here. So let's use the product rule. So if you use the product rule, what's going to happen, you take the derivative of the first term and then you have the second term as it is. So the cosine 2 ln x plus c2 sine 2 ln x. Now we take the derivative of the inside function. So that means which is x to the 1/2. So let's take the derivative of the inside function. If the derivative of the first term is a cos, that means it is sine, so it's a negative. It's a cosine term. So if you take the derivative of cosine term, it's become negative sign. With the negative sign, it's become positive. So we have positive sine 2 ln x times the derivative of the inside function. Derivative of the inside function is 2 1/x. So it's a 2 1/x plus, now do the other one. So you can see it is c2, derivative of sine means cosine, and then you're going to get as before 2 ln x times 2 over x. That's what you get. Now as before, what we're going to do, we're going to plug in the initial condition. So using y prime 1 equal -1/2, we're going to get, you can see that we're going to get negative 1/2 equals to 1/2, because you plug in x equal 1, so you get 1/2. And in the first term, you can see that if you plug in ln equal 1, it is 0, so the cosine 0, so you're going to get negative cosine 0. Cosine 0 is 1, so you're going to get negative 1, plus the other term is simply 0 because ln 1 equals 0, so 0. And then you're going to go to plus. In the second term, what's going to happen is the first one is 1, and the sine ln 1 is 0, sine 0 is 0, that means it's going to go away. So plus, this is going to get c2 as before. This term is 1 times, you're going to get that 2. So now we can simplify this one. So once you simplify this one, what are you going to get? So you can see that negative 1/2, they get cancelled. So this says that c2 equal 0. c2 equals 0. So therefore the solution. Therefore the solution to the initial value problem is, y equal negative because c1 is negative, so negative x to the 1/2 cosine 2 ln x positive, x positive. So that's the solution. That's what we get as a solution for x positive. So let's see how the solution of such a equation looks like, but not just for this one, but some other numbers. So for example, let's see what happens if you have negative, if you have x to the 1/2 cosine 3 ln x instead. So let's look at the graph of such functions, because it's a good thing to kind of remember. So you can see that this kind of equation, for example, the first one. So the first one is x to the negative 1/2 cosine 3 ln x. If you have cosine 3 ln x, so what's going to happen? So this is a kind of typical graph, and you can see that when the time passes, it's going to decay. So this is a decay model. So it's a decay. It's going to decay. So it's like if it's an energy problem, it's lose the energy, so the system lose the energy, and it's going to decay. So the y gonna stop. And then if you had x to the positive 1/2, so what's gonna happen? It's gonna explode. So so it's a growth model. So you can see. So it is a growth model. And then if a system has this cancer, it's gonna create a large energy, and probably the system gonna break in this situation. What we normally call it's gonna go to a blow up solution. It's called blow up solution. So so we do not like that kind of solutions for a real world situations, because it's not gonna stay for a long time, because it's gonna grow indefinitely. Okay. Yeah, so this is pretty much what we want to discuss, but so there are some other situations as well. So but we're going to discuss those things in a future discussion. So we can say in another lecture, we solve more general equation. We solve more advanced equations, such as, so we can solve equation like this: x to the cube y third derivative plus 5 x squared y second derivative plus 7x y prime plus 8y equals 0. So the idea is the same, but in this case what we normally use is, so we're gonna say we're gonna use x equal e to the lambda, and find equation in lambda. Find an equation in lambda, and then after we get that, then we know how to write the general solution. So that's how we're gonna do problem like that. And then we can also handle a problem like this. So let's say x squared y double prime minus 3x y prime plus 3y equal, let's say, like some numbers, 2x to the fourth e to the x. So if you get a problem like that, there is a special technique, what we call the variation of parameters. We can use that method. So we can use a variation of parameters. Variation of parameters to solve that. Variation of parameters method. Good. And also we can consider a problem like that. So x squared y double prime minus xy prime plus y equal ln x. We can again use the variation of parameters to solve a problem like this. So we can use the variation of parameters again. So use variation of parameters. Yeah, so we can see them in a future discussion. Okay, so this is the end of the Cauchy-Euler differential equation discussion.